This week we're going to talk about waves. And when we talk about waves, we're talking about a totally different aspect of physics. Most of physical phenomenon can be separated into two distinct divisions. One division is the particle division, which is what we've been talking about up to this point, where we're talking about things that are particles in space that move or have certain forces impact them. The other major subdivision is the subdivision of waves, and we're going to start today talking about that. So we need first of all to talk about the terminology. A wave is a periodic motion or oscillation that transmits energy. Now there are essentially two kinds of waves. There are mechanical waves, which are waves that require a medium to be transmitted, and then there are electromagnetic waves, which are waves that do not require such a medium. A medium is any substance through which a wave can travel or transfer its energy, and air is an example of a medium. Water can be a medium. A rock can be a medium. Anything in which will conduct or allow for the transfer of wave energy is considered a medium for a mechanical wave. Now, when we talk about waves, we talk about certain aspects of the wave. A wave pulse is a motion that causes a wave to go through a medium. Think in terms of, say, a rock falling into a pond. That contact that the rock makes with the pond is the wave pulse that initiates the motion of the wave through the medium, which in that case is water. A wave train, on the other hand, is a series of waves, one right on top of the other. You can see here, what's pictured here is an example of a wave train because there's more than one wave present. And this wave train can be initiated by a series of periodic motions or other things that just think in terms of somebody dropping several rocks in the water sequentially very close together, and you get the idea of a wave train. The crest of the wave, as pictured here, is the top of the wave, and the trough of the wave is the lowest part of the wave. So the high point of the wave train is called the crest. The low point of the wave train is called the trough. However, I will point out that in describing that, we're describing the definition in terms of a transverse wave, which I will talk about some more in the next couple of slides. There are actually two kinds of waves, transverse waves, two kinds of mechanical waves, transverse waves and longitudinal waves. And when we talk in terms of the high point of a wave train and the low point of the wave train, we're actually talking about transverse waves. So this diagram shows you the difference between a longitudinal wave and a transverse wave. To get the idea of the definition, a transverse wave is a wave where the direction of the wave, in other words, the direction it moves as it moves along, is perpendicular to the oscillation. In this case, the hand is moving up and down, and the direction of the wave is from left to right. In other words, it moves from left to right. The wave impulses or wave train moves from left to right. However, the oscillation moves from top to bottom, which is perpendicular. So that is a transverse wave, and in that system, the peak or the crest is the top of that wave train and the trough is the bottom. Now a longitudinal wave, on the other hand, is pictured below that, and it's where the oscillation and the direction of the wave motion is parallel. So you see that there are compressions and rarefications, and those are in the same direction as the direction that the wave is moving. So at certain points, the impulses come closer together, and it's the compression of the medium in the longitudinal wave, and this corresponds to the crest of a transverse wave. And then there's rarefaction, or called in the diagram expansion, which is the spreading out of the medium in a longitudinal wave, and this corresponds to the trough. To state this again, to make the point, because many people don't think in terms of longitudinal waves when they think about waves, the compression pulse is the crest and the rarefaction pulse is the trough. And from compression to compression constitutes one complete wave. Now, other parts of the wave that have terms that we need to become familiar with include the idea of the wavelength. And the wavelength is the distance from crest to crest of a wave. So this would be the distance from compression to compression in a longitudinal wave, or the distance from crest to crest in a transverse wave. The amplitude is the maximal distance or maximum displacement of the oscillation from the baseline. Now here the baseline is shown as a dashed line through the middle of the wave, with an equal amount below the line of the wave below the line as above the line. And the distance y shown here would be considered the amplitude of the wave, and it would be equal to a negative distance at the trough. The frequency is the number of waves that pass over a given period, pass through in a given period of time. So that is, if you say how many wave impulses pass in a second, then that's a frequency expressed in the time period of a second, sometimes called cycles per second. And there's a term known as hertz, which is another way of saying cycles per second. The period is 1 over the frequency, so it's the time it takes for one wave pulse, one full wavelength to pass a single point. And so the period is in seconds, and the frequency is in cycles per second. The speed of the wave is the rate at which the wave travels through the medium. So just to keep it straight, the period is the time required to complete one cycle. The frequency is the number of complete cycles in 1 second. And they're related to each other in that frequency is equal to 1 over the period. Lowercase f is usually used to designate frequency, and capital T is usually used to designate period. And the hertz is the System's International Unit for frequency, and it represents 1 over a second, so it's cycles per second. The period is the inverse of the frequency, or the time to complete one wavelength, and it's generally labeled with the term seconds. Now, the wave equation is actually the only math we'll be doing in this week, and it's very simple and straightforward. A wave velocity, which is the velocity at which the wave crests or other parts of the wave move, and it's not necessarily the velocity that the particles within the medium move. The wave velocity is equal to the wavelength over the period, or the wavelength times the frequency. So it's the time it takes to go through one wavelength, so that's the wavelength over the period, but it's also equal to the wavelength times the frequency. So the speed of the wave is directly proportional to the wavelength and the frequency. So if you keep, what that means is that velocity will increase if the wavelength increases and frequency is kept constant, or velocity will increase if the wavelength, or if the frequency is increased and the wavelength is kept constant. So both of those are directly proportional. And the formula is V is equal to little f times lambda, or frequency times wavelength. So let's take a look at a couple of problems of this wave equation. They're pretty straightforward. The first problem says, what is the velocity of a wave with a frequency of 760 hertz and a wavelength of 0.45 meters? Once you get out a piece of paper and get an answer for this, and then we'll go over it. And if you have to stop the tape in order to finish your work, then you can do that. The second question, a wave has a velocity of 345 meters per second and its frequency is 2050 hertz. What is the wavelength? Again, work that out on a piece of paper and see what you get, and then we'll do the problem together. And if you need to stop the recording so that you can get this done, then do so. Okay, let's see how we would do this first one. We said that the velocity is equal to frequency times wavelength, and we are told that in this situation the frequency is 760 hertz or per seconds, and the wavelength is 0.45 meters. So if you look at the dimensional analysis here, you're going to end up with meters per second. So if we do the math here, we get 342 meters per second. Now, to two significant figures, it's 340 meters per second, and that would be the best answer. The second problem, we're given the velocity and the frequency and asked to find the wavelength. Well, if V is equal to the frequency times the wavelength, then the wavelength is going to be equal to the velocity divided by the frequency. So it's going to be 345 divided by 1050 or 2050. And both of these have three significant figures, so our answer should come in three significant figures. So the answer is 0.168 meters, and that's the wavelength. This would be meters per second, and this is per second. The 2 seconds cancel out, and you're left with meters.